Okay, have you tried it?
I haven't. Shouldn't be in series black to red.
Yes.
Your name is Victoria, right?
Yeah.
What's your last name?
Green.
Okay.
Just grab a second.
Did you work with Ethan Thompson?
I think so.
I think so.
Yeah.
And Lauren?
Yeah.
I actually tried just one 9-volt and they all flipped.
Okay.
Yeah.
So let's just use the one 9-volt. It must have been just not a good circuit, but if we can get something rigged up. Well, I don't know. It seemed to work okay.
No, I think.
It's almost like there's a
Okay, thank you.
almost like something got magnetized nearby. Because they're still,
Are they just torquing to each other?
maybe.
Yeah, I think that's what it is.
Yeah, that's what they're doing. So dang it, we're out of time. Okay. Good morning, folks. Are we live on YouTube?
Yep.
Okay. So take off where we left off on yesterday. Let's see. And the magnetism comes from moving electric charges. And if we have a wire, I'll just pull one of these off. The magnetic field produced by a current going through this wire is going to be the form of circular loops, with the magnetic field being weak far from the wire and strong right near the wire. And if we use the convention that current is the flow of positive charge, what we call electrical current, say if it's going upwards in this wire, The direction of the magnetic field is if you point your right thumb in the direction of the current, your right hand will curl in the direction of the magnetic field. So looking at it from above, the magnetic field is in loops going this way, or counterclockwise or Widdershins. And if the current is going down, the magnetic field is then clockwise. So we use the convention of our right hand to determine whether or not we have clockwise loops of magnetic field or counterclockwise loops of magnetic field, where our thumb is always pointing in the direction of the electric current. And to illustrate that, we have a little demo here. Can we get the camera up so we can view this? We have basically a rod here. We're going to send current from this 9-volt battery through. And around this rod are a bunch of teeny compasses. And you can see they're pretty much all pointing towards north right now. But if I send electricity through that post, you see the compass needles flip. And now they're all pointing, it looks like counterclockwise. Is that clockwise? Yeah, that's clockwise. So the current is, in this case, going down. So we point our right thumb downwards, and our right hand will curl in the direction of the magnetic field. Okay. So that's where all magnetism comes from. Oh, do we want to do it again so the folks out here can see?
Yeah, I do.
Sorry. So let's do that again. So we got is that showing up okay? We're getting some glare. And we hook up the circuit. And you can see that the compass needles are all now pointing clockwise. Okay, that's good. Okay. Well, we could do some other cool things with this idea. If I were to send electricity through this loop of wire here, everybody see that okay? This will turn into a magnet. Again, we got the wires looping around so that the magnetic field adds in the center. And I can do it by hanging this loop of wire from these paper clips attached to the battery. That'll provide a complete circuit so we get electricity going from the battery through the wire. But this ring down here at the bottom is another magnet. So what happens when two magnets get close to each other? Anyone?
Don't they repel?
They could repel. They could also do what?
Attract?
They could attract or repel. Who was that?
Alexis Runger.
So basically, there's an alignment.
Yeah, they could push or pull or align. And let's find out what happens. Set that on there. I had this working just a bit ago. Yeah, I just needed a little bit of a push. You see the wire loop spinning?
It's kind of hard to see on this.
How's the video showing up on the computer?
About as good as we're gonna get. You can
Okay.
tell it is spinning now.
Okay, it's spinning around. This is called an electric motor. You send electricity through a loop of wire, and if you do it right and it's near another magnet, you can get it to spin. Now, it was mentioned that it should align. Normally, you think you've got like a north pole with my fist over here and a south pole with my fist over here. You'd think that they align. Well, what's happening here is kind of hard to tell unless we look real close. On one side of the loop, I've shaved off both of the little leads there, shaved off all the enamel. But if we turn it over, you see that one of those leads sticking out to the side has still the enamel coating on it. This is enameled magnet wire. The paint, the enamel paint acts as an insulator. And so by having one half of one wire with the insulation still there, this is only conducting electricity half the time. So it's only a magnet half of the time. So say if this is the fixed magnet, say a south pole, and this is the north pole, my fist is the north pole of the moving coil. It'll be pull, 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 but once it gets to here, now that post is resting on enamel and the electricity shuts off, and its momentum will carry it until it gets to over here, and then suddenly, boom, right about here, the electricity turns back on and it's pulled back. And then the electricity turns off and it coasts. So we only have electricity flowing half the time such that it's always being pulled just in one direction instead of being pulled this way and then being pulled back. And in real motors, this is not how we do it. This is very inefficient to only have electricity going half the time and only having an influence half the time. In real motors, what's done is you switch the direction of the electricity. So if this is a permanent south pole and this is a north pole, you'll have it so that the coil is pull, 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 until it gets to here. And then you switch direction of the electricity so that now my fist over here is the south pole that's pushed away. When it gets to over here, it switches again so that now this is a north pole and it's pulled back.
So does that with alternating current?
You could do it with alternating current, or you could use what's called a commutator, some mechanical device that will switch the direction of the current. And real motors don't just have one coil of wire and one magnet. They'll have 4, 6, or 8 coils and 4, 6, or 8 magnets, so that a coil is pulled towards one magnet while being pushed away from another nearby magnet. And as soon as it passes one magnet, the current switches, so it's pushed away from that magnet and pulled towards the next one. So you won't have just one magnet, you'll have like magnets, like 4 of them, north, south, so that the coil is always pulled towards one magnet and pushed towards the one it just passed, pushed away from the one it just passed. And so you can do that naturally with alternating current. It'll switch the direction of the electricity as the thing spins. Or you could do like what we have here. In that I have 2 fixed coils here. These will both be magnets. And the coils in the center, electricity will go into these coils from this paddle to this paddle. So electricity will always go from the red coil to the black coil. And the red coil, the way it's hooked up, is going to be a north pole right here. And this is going to be a south pole. This is always going to be a north pole. This is always going to be a south pole. But that means that this coil over here is going to be attracted to the coil, the black coil over here, and repelled from the red coil. But as soon as it gets to here, now current is going from the black coil to the red coil. And so now this is the north pole. And it's pushed away from this coil and pulled towards that one. So basically, whatever coil is on my side is going to be pushed away from this coil and pulled towards this coil. And whatever coil is over here is going to be pushed away from the coil on my left and pulled to the coil on my right. So let's give that a try. Oh, I had it backwards. Okay, it's going the other way. But same idea. And again, this is not a very efficient motor in that it only has 2 fixed magnets and 2 magnets that could move. Real motors, again, will have like other magnets nearby. And the separations here are actually kind of large. This is really only good for demonstrations. And it's not very efficient because the attraction of 2 magnets like this falls off as 1 over the distance cubed. So if you double the distance, you reduce the force by a factor of 8. So it's actually falls off quicker than the inverse square law forces we've been dealing with, say, with the electric force or with gravity. But this is how all motors work. Anything with a motor in it, a fan, like a hair dryer, a power tool, table saws, even the electric motors in cars, your leaf blowers, all of them work on the same basic principle. You send electricity through loops of wire, and they'll be pulled and pushed by usually permanent magnets to make the whole thing spin. And we can do some other cool things with this idea too. I have a rather ingenious device here. It is a loop of wire glued to a box. Okay? Actually, do I want to? No, let's not do that one just yet. Let's play around with these guys. Okay, what I have here is I have a power cord and I have a jumper battery, a car battery for jumping. Keyword there is jump. If I send electricity through this wire, it'll become magnetic. It'll produce a magnetic field. And it's going between a bunch of fairly strong ceramic magnets. And these aren't the same magnets, but the first magnets I got were this type, were actually donated to me, actually donated to the physics department from a student in this class almost 20 years ago. Interesting story. She ran and still runs a local holistic health clinic. I will not name her nor the name of the clinic, but she used these magnets of this type in little pillows that she would then pile around a person for magnetic therapy because, well, magnetism heals, you see. Yeah, but taking my class, it seemed like I was actually quite pleased when she first started, when she presented me with the magnets and said that I'd like you to have these because I've been using them for magnetic therapy. Well, I could say a few things about magnetic therapy in that, for one thing, we are transparent to static magnetic fields because it has no effect whatsoever on our physiology. So it's pure and adulterated quackery. And static magnets, piling a bunch of these magnets on top of a person is not going to make them feel better unless they want to believe that it makes them feel better. It has no absolutely no physiological effect. But anyway, so she was going to get rid of them, and I thought, great, she actually learned something. And then she shattered my illusions by saying, after taking your class, I realized that magnetic field is another type of radiation. We call it electromagnetic radiation. And she just, in not any consciousness, exposed her clients to radiation. So she had to get rid of the magnets. I went home and drank half a bottle of scotch after that. I was so depressed. She also got rid of all of her color gel filters, which are these wonderful theater gels they use in stage lighting, because she also had a whole series of light therapy where to treat various disorders and afflictions, she would shine different colored lights on people. And she realized from this class that light is electromagnetic radiation, and she couldn't expose her clients to radiation, so she had to get rid of those too. Yeah, that was a bad day. But I got these wonderful magnets I could use in demonstrations. So I've got a wire here that's going to carry a lot of electricity, and it's going between a bunch of magnets. What do you think might happen? Anyone?
It should jump.
Oh, this is the jumper cable. Ah,
Nice.
did you see that? Let's do it again. Yay! So electricity going through a wire makes it magnetic. If it's near another magnet, it's going to get pushed in one direction or another. In this case, yay, it jumps. I could do something similar with these rods here. I have two steel rods, and now they're on either side of a whole bunch of these magnets. And I can take a brass rod and set it between them. So that when I flip the switch, I'll get a lot of electricity going up one rod through this brass rod and then back. So I'll have electricity going through this rod that's free to move, and it's right on top of a bunch of magnets. What do you think might happen? Anyone?
It's gonna roll.
Roll! Okay, it rolled as far as it got to one magnet edge. Let's try that again. There we go. And away it went. Looks like we're going to need to buff these guys down. That wasn't conducting very well.
Okay.
With this sparking and arcing, we get some oxide built up on these rods. Here's aluminum. This is a bigger rod, it's thicker. So it should have less electrical resistance, but not by much. But aluminum isn't as good a conductor as brass, but it's a lot less massive. So the same force, we should give this a larger acceleration, but the force is going to be less because it's not as good a conductor. Will this go faster or slower? A little faster. It turns out that the mass is a bit more important here. Okay, so that was kind of fun. So I'd like to switch to a PowerPoint slide at this point.
Okay.
So remember, we can get a compass needle deflecting. Oh, by the way, who was that that says it would, the jumper cables would jump? Do you remember?
I don't know.
It was Crystal Sheath.
Okay. Okay, so consider this question. A compass needle is placed directly over the circuit shown below at points P, Q, and R. So we got a battery here, using the same symbol I had the other day. We have no resistors, but the wire goes up to P, over to Q, down here to kind of do a loop, and then back to R, and back over to here. So basically rank, this is like a ranking task, rank the deflection of the compass, or basically the strength of the magnetic field, at each of these points in descending order. So whichever is going to have the biggest, strongest magnetic field, rank first. So is it PQR, is it QRP, RQP, etc.? I think I've listed all possibilities. So think about this for a bit.
I think I might be missing a card. Oh, no, it's just in the wrong spot.
Okay, folks, you've had a chance to think about this. Show me your cards or type something down in chat.
Mix of A, B's, and C's.
Any Ds?
Or D's. Or F. E or F.
Oh, there's a D. No, instead of B, that's a B.
That's a B. Yeah.
So we have A, B, C, E's. I don't see any D's or F's. Is that right?
Yes.
Okay. So can I get a volunteer to defend why A is correct? That P has the strongest field and point R will have the weakest field. Someone want to volunteer to defend that? We have quite a few folks choose A, so please speak up.
Hello, can you hear me?
Yes.
I said A because I just kind of went by. I thought that like the strength of the field would get weaker later in the circuit, so I just went P was the first point, Q, and then R was the last one.
Okay. So we should have less electricity the farther in the circuit we get. And so the strongest current means the strongest field, and that'll be point P, and then Q, then R. Can I get a volunteer to defend B, please? The Q is going to be the strongest, then R, and then P. Quite a few folks chose B, so please, one of you speak up.
I could give this one a shot.
Please do.
So I figured that with the more turns or like loops in the wire, the stronger the field would be. And seeing as Q is kind of close to that part where it kind of turns around completely, and then at R where it does like 2 turns, then I figured P would be the weakest since it's just a straight path, not close to any of the loops.
Okay, so the field's going to be strongest where it's closer to the most wire. And so we've got a lot of wire kind of in this region. And we have then a couple of wires over here and only one wire over here. Okay? Can I get a volunteer to defend C? Again, we have several folks choose C, so please, somebody speak up.
Oh, someone else can go. Someone else talking.
No, please do, Alexis, go ahead.
Okay. I kind of did C just for the reasonings of B, where R is a little Q is a little closer to the loop compared to R, but I just felt like since R was after the loop, it would be the strongest, and then Q, and then P.
Okay, so here we have 2 wires that are really close together. Here we have 2 wires or a couple wires that are sort of close together, and here there's just the 1 wire. So
Yeah.
It's because the field gets weaker the farther from the wires, we should have a stronger field than R. That's what you're thinking.
Yeah.
Can I get a volunteer to defend E then, please?
We have a volunteer on class.
I see. Anybody online?
Nobody online, thank you.
Oh, okay, Mr. Crossgrove.
I chose E because I went with where the magnetic fields add in the same direction. I thought it would be the strongest. So since Q has 2 wires, or a wire that's fairly close to it and it's going in the same direction, it would add to it and be stronger. And then P, because it just has the one magnetic force, and then R has one going in one direction and another magnetic field going in the opposite direction, therefore canceling it out a little bit, making it less than P.
Okay, so the argument is here at R, yeah, we've got 2 wires close to each other, but with the currents being in opposite direction, the magnetic fields from each are going to be in opposite directions. So they would kind of cancel here. And here, the 2 currents that are close to Q are kind of in the same direction, and so they could produce fields that will add together. Well, over here, P is kind of off by itself. And so Q should have the stronger field because you got another wire nearby with current in the same direction. Okay, nobody chose D or F, and I will just state that those 2 are not correct rankings. It's either A, B, C, or E. I'd like to hear some discussion because it was not a clear majority for one of these or the other.
Okay, we're just gonna go right now and say, in the experiment, and all our results indicated that in a circuit where all of the components are working properly, there is no change in electrical flow across the entire circuit. So the argument for A that it gets weaker as it goes along the wire, we kind of already disproved.
I'm sticking with my case for E because I think it makes the most sense in my mind still.
And I chose C just because the wires are not closer together. So
What's it look like on chat? Any comments?
I didn't think the direction of the current. I like the argument for E. The explanation for the answer B made sense to me.
Is that it from chat?
That's it.
Okay, folks, we've had some discussion. Go ahead and show me your cards or hit a letter on chat. What's it looking like on chat?
There are now E's on chat with A's, B's, and C's.
Okay, which is the more common response?
C,
Looks like C. Okay,
maybe E.
maybe E.
It's pretty close between the two.
Okay, because we've got 3 folks in class doing E.
So 1, 2, 3, 4 C's, 1, 2, 3, 4 E's on chat.
So we have 7 E's and, okay. Yeah, so E is the most common opinion now, and that in fact is the correct answer for pretty much the reason stated, in that direction is important, in that 2 currents in opposite directions are going to produce opposite directed magnetic fields. Now, the fact that they're offset a little bit, let's see, makes it a little bit more complicated, but not significantly more. So if we look right at P, we've got a field I'm going to say is into the board. Sorry, a current that's into the board. I'm going to use a little X with a circle to distinguish that. And so if we stick our thumb in the direction of the current, the magnetic field right above is going to be in that direction. If we look at point Q, oh, what does it look like? Okay, we have fields in 2 directions. Sorry, we have the current. Okay, the one current is going to produce a magnetic field like that, and this other one is going to produce, let's see, right angles. It's going to be a little bit weaker because it's farther away. So the net magnetic field is going to be not just to the side, but it's going to be up and to the side. And then at point R, the pirate point, we're going to have a field trying to make this about the same length, but then here is going to have a field a little bit weaker, but it's going to be off in that direction. So the net magnetic field is going to be off in this direction. And will be a shorter vector than any of the others. So we have a little bit of cancellation going on in R. We have mostly addition going on at point Q, and we just have something straight at point P.
Just one question.
Yeah.
So, have you determined the vertical orientation of the wires for this?
Okay, in my drawing, I'm just having the wire, imagine the wire going into the board, so like this.
Okay.
And the magnetic field at point P is going to be that way. And then here I've got the 2 wires going like this direction. And so the currents are going in this direction.
Okay.
Okay, so basically into the board is like off to the right on that figure.
Okay. Makes a little bit more sense.
Okay. Let me show you a couple of other possible motors. Do we have a Lorentz motor?
Yes, front corner there. On the desk by the remote.
This is a homopolar motor.
Oh, Then I don't have a Lorentz motor. I have a homopolar motor.
Oh, you didn't get both?
No, I just grabbed the one.
Okay, well, here's another example of a motor. Got a battery here, and it's sitting on top of a magnet. And if we provide an electrical connection between the top of the battery and the bottom
I see this.
through that magnet, we can get it to spin. These are very temperamental motors. I made a bunch over the summer for a bunch of fifth graders. But if we turn the magnet around, I think it might work a bit better. Maybe.
I think it just got a weird amount of friction.
Yeah, we got a lot of friction. It's not as well balanced as it could be. But okay, it turned for a little bit. Okay. So there are lots of different kinds of motors. But we could do other cool things with this idea besides making a motor. Let's get back to this guy I started to talk about. So what I have here is I have a loop of wire and it's glued to a box. Okay. What do we call such a wonderful, marvelous piece of technology? Anyone? If I send electricity through that loop of wire, that'll become a magnet. Everybody okay with that idea? Any thoughts on what we call this? Okay, so if I send electricity through that loop of wire, magnet, and I bring another magnet nearby, I've got a pretty strong one right here. Depending on the direction of the current, that wire loop will either be pulled towards the magnet or pushed away. Any thoughts yet on what this is? Okay, what if I send a signal that changes direction? Say an alternating signal, kind of like what I had through that LED I had yesterday. If we switch the direction of the current, it'll be pulled towards the magnet and then pushed away. So if the current's going one way, it'll be pulled towards it. If it's going the other way, it'll be pushed away from it. So if I send a signal, say that it changes direction 60 times a second, like wall current, this thing will be pushed back and forth. It'll vibrate 60 times every second.
So, oscillator.
You could call it an oscillator, but there's a more common term for this that should be more familiar. What?
Or a speaker?
A speaker. Very good. Because if it vibrates at that frequency, it'll vibrate the box at that frequency, vibrate the air at that frequency, producing a 60 hertz hum that you could clearly hear. But if we send a signal that's a bit more complicated with lots of different frequencies, remember we talked about the recipe of sounds? Yeah, it's a speaker. So let me play something from this century. I heard these guys in Austin back in 2004. No, 2014. They produced their first album a year later. And I'm not sure it's.
Did you disconnect those?
The amp is off.
What?
I believe the amp is off.
Okay, let's turn the amp on.
And then you'll need to connect the alligator clips.
Right, I know that. And they're tied in a knot. Okay. Okay. Let's see, we have sound? No. Play. Play. Okay. Okay, hear anything? What are we missing?
Don't you need to-
Yeah, let's turn up the volume. a magnet? Oops. Maybe not that much. Should I blow this thing? Seems to be having problems with power. Does it normally fade out like that? It's like it's turning on and off here. Did you test this?
Yeah, it was functioning just fine this morning.
Okay, quickly grab that one, please. I think I turned the volume up too much. While we're waiting, I have another similar device. This solo cup speaker has a loop of wire glued to it, and this speaker has a magnet stuck to it. The two together. Oh, it's a brand new one. Just
Yeah, I don't have any other in the demo room.
okay. I wonder if the jack will work for this. It should. It's the same voltage, I think.
And you just need the magnet, right?
Well. Oops. There we go. Okay, so it's hooked up. Hopefully it's ready. And go ahead and turn it all the way up. Is that the auxiliary? It should be.
Yeah.
Oh. I'm going to try a weaker magnet. Yeah, I can turn it up. Just being cautious here. Oops, that was too much. I heard it cut out. So turn it off, turn it back on. Okay, it's cutting in and out, so I think. Oh, we have a short someplace? No. Okay, try again. Yeah, louder. You should be able to handle it. No, it's cutting out. Okay, but did you hear that? Okay, we got the amplifier problems here. So, but that's a speaker. That's all there is to a speaker. You send electricity through a loop of wire, and if you send a signal at the same frequency of the sound you want, it's going to vibrate at that frequency. And that's how all speakers work. So, home improvement tip. This is what I tell the fifth graders when I did this workshop over the summer. You get a big loop of wire, you could hot glue it to the wall of your bedroom. Get yourself a nice big magnet and think of what you could share with your friends, family, and even neighbors if you have an outside wall. So people do this to the trunks or hoods of their cars. Basically turn the car, their chassis, into a big giant speaker. Or they'll do that to like one of the boards over the trunk. Or even some sort of residence board in the back seat instead of a back seat of the car. Has anyone seen a car rigged up like that where they've done that to like the hood or the trunk? Okay. Well, maybe that was a 1970s thing because that was real popular back then. I guess I'm dating myself. Okay. And well, something that's kind of let's do this demonstration. This is something that was just put together. And let's see.
Yeah, they clamp on the
Let's do it the other way. And we have two wires here. And if we flip the switch, no, don't flip the switch. We could either send current through these wires where the currents are going in the same direction or going in opposite directions. And this is where I'd like to slide up. Okay, so this is the question. When electric current in two parallel wires is flowing in the same direction, what do the wires do? Knowing that, they both produce a magnetic field, and these magnetic fields will affect each other. Will they repel, attract, exert no force, twist at right angles, or in fact spin? Those are the possibilities. I'd like you to think about this for a moment or two. Do you remember which way the switch has to be to make them go parallel? I don't know for sure. We ought to have that labeled on here. This is the very first time this device has been used. So we're going to have this discussion, and then we're actually going to do the demo. What do you mean backwards?
pull the switch back to make them go the same way.
Okay, pull it basically that direction to the north to make them go the same direction. Okay,
5 minutes left.
I know.
Sorry.
Okay, we've had a moment or two to ponder this question. Go ahead and show me your cards, what you think might occur.
Mostly A's.
1C.
1C.
Only one C?
Yes, I believe so.
Okay. So could I have someone defend C, that there should be no force? Anyone?
If I was the only one who chose C, I think, I chose that they wouldn't exert a force on each other because they would be independent of each other. I don't know if that makes sense.
Okay, by independent, what do you mean?
Meaning one wire would not cause a force on the other wire.
Okay. Can I get a volunteer to defend A then, that they should repel?
I was thinking since they're both just parallel lines, they're both gonna have the same charge, so they're just gonna repel each other.
Okay, so the current in the same direction means they have the same charge, that should repel? They should repel then?
Yes.
Okay. Does anyone have anything to add to this? Okay, since it was virtually unanimous, I don't think we need to have some discussion. So are you sure that it's, if we flip the switch that way, they're parallel?
I'm pretty sure, yes.
Okay, so let's see what happens. Oh my goodness, they attracted. Do it again. My goodness, what could be going on here? Do we have time to talk about it? Yes, we do. Well, by having electricity going through these wires, we do not charge them. They have been and are continuing to be electrically neutral. There is no electric forces involved here, but there is a magnetic force. If we look at the magnetic field produced by each, let's look at the field between them, because that seems to be where the interaction is going on. If they're going in the same direction, let's say it's upwards. Okay, looking at it, looks like the current's actually going downwards. Okay, so if we have current going down in both of these wires, the wire that's on your right will produce a magnetic field. If you stick your thumb in that direction, will go into the board. So the magnetic field from the wire closest to me is going away from you. The magnetic field from the wire on the right, stick your thumb in the direction of that current and curl your hands, it's going to produce a magnetic field in the opposite direction, out of the board. So these two wires, right between them, are producing magnetic fields in opposite directions. If we have two magnets that are producing magnetic fields in opposite directions, that's because their poles are oppositely aligned and they're going to pull together. So that's what's going on here. This is like having one magnet with its like north end up and the other with its north end down, and they're going to pull together. That's kind of like what's going on here. So that's pretty much all the time we have. Thank you for your attention. We're going to continue with this discussion because there's a lot more to the interaction between electric fields and magnetic fields than we've been able to talk about. We can actually create electric fields by changing a magnetic field and vice versa. So thank you, folks. So the only demo I didn't get to was the electron beam. And maybe we have this out again tomorrow. We'll show that we have them anti-parallel that they'll repel. So maybe let's have this play out again.
Yeah, in the switch in the neutral position, it doesn't conduct any current. You can leave the battery on and then just have.
Oh, that would be a better way? Okay.
So, I mean, whatever works best for you, particular matters, but